Last time we talked about how breadth first works, or not exactly just breadth works, but how breadth and deep first work, and how they are optimal in their sense. As in the depth first can work very fast and in a finite number of nodes, and it dwells the deepest possible in the node. So if the node is very deep, then it's pretty much a better solution than well than the breadth first. And how breadth first also works in an infinite number of nodes, and it slowly creeps away in absolutely every single division. And because of that, it's very optimal if the solution is closer, or again, is infinite. But there's something that we haven't thought much. That is that all of these solutions are based if we again don't know. We don't know where it is. We don't have any um, information about it, which is not always the case. Again, but just see, search the search algorithm that always spend the deepest node in the frontier and the shallowest node in the frontier. But again, all of these are in the assumption that well we are making an uniform search, or all of those are uniform search strategies. As in, it's like we don't know nothing. I mean, we don't know where the node is. Our examples don't give justice, really. The examples we have given, not just me, but I would say it doesn't give justice because the computer pretty much only sees the frontier, meaning the puzzle piece right in front of it. But if you could have more of a macro vision, meaning you could have a vision of where the node is, then it could make a more informed search. So that's pretty much what you're going to do with the greedy best first search. A search algorithm will expand the node that is closest to the goal as estimated by the heuristic function. Now, to understand what the grid best first the search does, we need to understand what the heuristic function is. Well, imagine again our simple puzzle here. Now imagine in this puzzle 2 points, let's say C and D. For us humans, it's obvious that C is it's much farther to point B than D. So D is the closest point. And this is very clear to us, but not to artificial intelligence. After all, to this puzzle to work, we can't just say, well, the closest considering the walls. We need to say the closest not considering the walls. After all, just would make the artificial intelligence do the what we want. And inside this grid with no walls, it's much obvious for us and the artificial intelligence that D is in fact closer. And then this number, pretty much the number of grids between D or C, for example, horizontally and vertically, not diagonally. It doesn't travel diagonally, just horizontally and vertically. It's called, again, the heuristic function. You can see here much farther, much clearer that D is in fact closer than C. And we can even see exactly how would the artificial intelligence see this. And considering this, we can make a simple puzzle, but with every single step we can take, every single action we can take, as a number. Or this is the heuristic function, or as the heuristic function. And we can see here much clearer that here, for example, right at the front of A, there is 16 tiles or 16 steps to go from here to B. And here, for example, you can see much clearer that it doesn't consider the walls. Here are just two steps, even though there's a wall in between. Again, this is an informed, meaning we know the layout, but we can just say to the artificial intelligence, oh, since you know the layout, you can already move. This is solving the puzzle. Here, we are just simplifying. And we can start, artificial intelligence can start thinking again. It will, of course, move to the closest possible, which is, again, the first tile or 16, uh, heuristic function of 16, and it will go naturally. But here is where it differs. As in breadth first or deep first, in case of the deep first, it will arbitrarily choose between left or right. And breadth first will not choose at all, we just keep growing. This is an actual choice. I can choose either, well, the going to the left, which increases my heuristic function, and going to the right, which decreases. And we want to get closer to B. Well, we want to get to B actually. So of course we're going to take the shortest route, and it will keep going until, for example, in this situation, where in this situation I have not just one but two choices that have the same number, and sometimes artificial intelligence will fail. But since the shortest number is 7 and not 13, again, artificial intelligence is still considering 13. But unless our number gets higher than 13 or equal to 13, then it won't in any way choose you. So we just go back to 7. And number 6, and then 7 again. This is a choice it needs to do, since, again, 7 is lower than 13 is the only choice, so it would need to increase its number, even if this kind of contradicts. It's still the lowest number. Now the lowest number is 6, then 5. Now we get into a problem. Our heuristic function says that the path 4, 3, and 2 right up that leads to an wall is the best path. Why? Well, because, again, it's closest. So it will try this, and, well, it will fail. But it will still prevail, and it will still have a very decent approach to the problem, going here until it hits B. So you can see that, well, it is a very optimal solution. Not the best, again, it did some little mistakes, but that's no problem in this type of puzzle, at least, because this part, from choosing this exact part that is, well, heuristically closer to B, made a mistake. And this mistake is, well, much more exemplified in a situation like this puzzle. Now this puzzle is interesting. Let me put the heuristic numbers so you see why. We have this path, and this path in specific has a lower heuristic number for most of it than this one, but it will need to close loop, and you probably now have begun to see the problem. It will slowly go until here, and here it's where the decision, well, it fails. It goes here, it's where you choose 11 instead of 13, and will keep going. It will keep going to this wrong route, in where the heuristic number is lower until here, and then it will begin to go higher and higher and higher and higher and higher, but not high enough to justify in the eyes of the heuristic functional list of our very best first search to go to 13. So we will go to 12, and then it will begin to slowly make its way to our goal, B. And of course, this is not the optimal path. This is definitely an optimal path. This is the optimal path. If it would choose to go here and, well, somehow we could say that this is the bad path, it would be in fact the best solution. But how how do we make as such that, or artificial intelligence chooses knowingly that this is the bad path? Well, this is going to be something to talk about the next video. But don't worry, we are not. This in case it's going to be a new search algorithm that, well, you could consider almost the ultimate search algorithm of the informed solutions. Almost. There is some little problems, but you will almost always find the best solution. So if you want to see it, subscribe and hit the notification bell so you will receive a notification when my video launches, so you won't miss it right at launch. Not just that, but like this video if you did, and again, uh, comment down below if you have any questions or, well, any ideas of how could any of these search algorithms be placed on the best problem they could be put, for example. But, well, I believe that's it. If you like and subscribe, hit the notification and comment down below, and I see you tomorrow. Bye.